Here we go. So looking at moving average models, they're used to model stationary data, but they are not as useful as AR models in modeling actual stationary data. On the other hand, they are very useful in conjunction with AR models. They fit together very well to form what are called ARMA models, which are used as an extension of the AR model. So it can make AR models more useful, which would be what really George Box would recommend for us, in that he says all models are wrong, but some are useful. Very popular quote. So that's our goal here, is to come up with useful models, and MA's moving average models will help us achieve that goal. So let's first briefly study the moving average model by itself. So here is the moving average model. Note that it's got thetas instead of phi's, and that those thetas are coefficients of white noise terms instead of coefficients of the x's. So here we have x of t, or x sub t, equals mu plus at minus theta 1 a sub t minus 1 all the way to theta q a sub t minus q. So again, it's a function of white noise. Each xt is a function of white noise here in this model. So the theta j's are real constants, and the a sub t's are white noise. So notes, xt at time t is a linear combination of past and present noise components, which might seem familiar and might seem amazing. That is, the MAQ is a finite GLP. Remember in our discussion of generalized linear process, or the general linear process, and is always stationary. So when we talked about the GLP, we said that was back in filtering. We said that it is a linear filter, and that this is the GLP form right here. X of t equals mu plus an infinite sum of psi j's times white noise. And that is exactly what the form of the MAQ model is. So we can very easily see here that a GLP, an MAQ is a GLP, and you don't have to do too much to it to see it. In fact, you don't have to do anything to it. So here we see, if you make psi naught equal to 1, and psi 1 equal to negative theta 1, and psi 2 equal to negative theta 2, and all the way to psi q equal negative theta q, those are the psi weights, the thetas. If you have a moving average model of order q, the theta q's, or the thetas in that model, are the psi weights. So let's look at a quick example. So that is an MA1, can't get much more basic than that. That is xt equals 4 plus a sub t equals minus 0.9 a sub t minus 1 plus 0 a sub t minus 2. Again, two things going on here. In MA1, the thetas are zeros for 2 and beyond, for t minus 2 and t minus 3 and so forth. So we just put one in there to show that they're zeros. You wouldn't usually show that one. But if I wanted to write this in GLP form, it's already in GLP form, right? We've got 4 there is the mean. We've got our AT, and our, so psi naught is still 1, and psi 1 is negative 0.9, so on and so forth. So great work. That is the GLP. Let's move on. So the zero mean form. So the zero mean form is very much what we've seen before. We're just going to plug in a 0 for mu to make it simpler for convenience. Operator, so we can see the properties and characteristics. The operator zero mean form, we can put the any MA model into operator form as well and zero out the mean. And the MA characteristic equation, and once we have that operator form, plug in z's for the b's, and we have our characteristic equation. It's very analogous to the autoregressive, the AR side, except the coefficients here are now on the white noise terms. So looking back, we've got this model. Let's say that we've got xt minus mu equals a sub t minus theta 1 t minus 1. This is a moving average. We've seen one like this. This is a moving average model of order 1, where q equals 1. Again, that AT is white noise. If we had operator form, we'd write it just like this, just like you would in the autoregressive, the AR side. And the zero mean operator form is like that. We're just zeroing out the mean so we can see the same properties and characteristics. We can easily add the mean back later. So the MA1 results, we want to say, hey, we want to look at the expected value, the variance, and so on and so forth. So the mean here, it's the same thing. It's a stationary process. So being a stationary process, the expected value of xt equals mu. Notice that there's no subscript on t there. It does not depend on time. Expected value of xt, no matter what the t, is mu. The variance also does not depend on t. Again, it's a stationary process, and this is the formula for that. It's sigma squared sub x equals sigma squared sub a, 1 plus theta 1 squared. So that's where the theta part of the model comes into the variance. Very easy to calculate in an MA1 model. The autocorrelations are rho 0 equals 1. That's always the case. But then rho 1 equals negative theta 1 over 1 plus theta 1 squared. And now this is very interesting, that theta k, or rho k equals 0 for k greater than 1. These are the true autocorrelations. You won't see these if you look at it from a sample point of view, and we'll see that shortly. But they don't damp exponentially. As soon as you get past q, the rho sub k's are all 0. So q here is 1, so we've got rho naught is 1, rho 1 is negative theta 1 over 1 plus theta 1 squared, and then from then on, the theoretical autocorrelations at lag k for k greater than 1 are all going to be 0. So that's going to become a real defining piece of moving average models. And the spectral density, we're going to talk much more about this in the future, but here is the functional form, and they will operate similar. They'll have some characteristics that are similar with AR1s and actually kind of directly opposite. Kind of a spoiler alert, the moving average spectral densities will have dips in them rather than peaks. And then this is the formulation of that spectral density formula. So great job. That was a lot about the characteristics and the properties of moving average models. Great job. I'll see you in the next one.